Hey, Jacob.
Hey Dan,
How's it going?
it's going well. How are you?
I'm doing okay. Pretty busy. Um, I had a little bit of trouble following the link to the Zoom meeting.
Oh no, really? Okay.
Um, it shows up in the meetup with like a carriage return in the middle before where it says PWD.
Oh no. Okay, I see.
Um, yeah, if I clicked it, it didn't work, but if I like copied and pasted it, it did work. Um,
Uh,
I'm not sure. I'm not sure if other people are going to have the same problem.
I had that problem.
Oh, okay.
So probably. So let me see if I can fix that. Thank you. Thanks for letting me know.
Yeah, I'm glad that I was able to find my way in here.
Yeah, me too. Uh, how you been? Yeah, I haven't seen you in a while.
Yeah, I am sorry to fall off of it.
It's okay.
I'm moving to New York in a week,
That's awesome. So you're not. Where are you? Where are you going?
so I'm going to Pratt.
Oh, that's really cool. Yeah, Pratt is awesome.
I'm pretty excited. Yeah,
I'm excited for you. That's going to be really,
thanks.
really cool.
Um, do you know anybody there or anything?
I know people who used to be there,
Oh, okay,
but that's it.
sure.
I'm having a hard time trying to figure out how to edit the event. Uh, um, uh, so, so when do you start then? You're in the fall then?
Yeah,
Okay.
so classes start the week before Labor Day, and there's this like 2 week long thing that they want all the architecture students to do, which is the first 2 weeks of August. And
Mm-hmm.
I can't tell if I'm going to know everything in it or not, but I'm going to do it because they recommend it. I think it's like, here's how to use Rhino, here's how to use the 3D printer, here's how to use the laser cutter, like just like basic stuff like that, because we're going to be relying on it really hard for the design studios, and they want to make sure everybody knows the real basics.
Mm-hmm.
Um, yeah, so I'm sure one way or another it'll be worth the time. Anyway, so that's the
Are they
beginning of
just
August. Hmm?
covering modeling stuff?
Uh,
Or
it's not actually super clear.
okay.
Uh, it does seem like almost all of the design is done in Rhino in their program.
Mm-hmm.
Um, so, but yeah,
That's
I
interesting. I
think
didn't
it's
know that.
yeah.
That
I mean,
yeah.
we're gonna find out how true that really is, but this is what I'm led to believe.
Yeah. Like it's weird to be. I mean, well, I guess schools aren't software agnostic in a way, you
They
know.
can't really be. I mean, they can try
Uh,
to teach you stuff that's agnostic to technology, but they sort of have to use some technology or other.
yeah, to just like narrow,
Yeah.
narrow it. Yeah, make it easier.
Yeah. When I was, studying engineering, the way they solved that was by teaching you using really outdated tools
Mm-hmm.
that weren't really useful for anything.
Mm-hmm.
But maybe we're better for teaching the concepts. But yeah, it sort of like kept people from focusing too hard on learning the ins and outs of the programming language we were using or something, because nobody was going to get a job using it.
Um, yeah, people are having a problem into. Hmm. Oh, hmm. Oh, Eric made it in. Oh, that's good. Dan, did you, you have to get the whole link, including the password section?
That's right. That's how I did
Okay.
it.
Yeah. Yeah. It's every time I see it paste correctly, but yeah, it's weird that it's in the link
Yeah,
with that return.
I don't know. Is there a way you can just, if you just paste the meeting link itself, like everything before the question mark, does that get you there, or does that like almost get you there and then you need a password?
It gets you there. Or I just did that. Actually, yeah, I should close this other. Actually,
Yeah. So why don't you just paste that and maybe it'll work.
Well, see if Nathan can get in. Yeah, I think maybe wait a couple more minutes and then just jump into it. But I'd like Nathan to come. I actually put some things in there for him because he works with acoustics and acoustic surfaces and
cool.
and all of that, and had a chance to do some ray tracing stuff.
You were doing ray tracing with Grasshopper?
Yeah, forward ray tracing, from like a point on the stage and seeing how those rays interact with and distribute sound.
Cool.
Sort of certainly in a diagrammatic way. More diagrammatic than in actuality. Yeah, that's obvious, but it's neat, because you do see, like, if you were to introduce a concave curve and how it starts to focus and act differently.
Yeah, what tool did you use for that?
I just used Ladybug, actually.
Oh, really? Okay.
Yeah, they have a forward ray tracing.
Okay. Neat. I haven't used Ladybug before.
Yeah, I started with just making cool, like, parametric stuff, which is sort of what I was going to present, but now trying to use that same strategy or parametric process for building performance, and using Ladybug as the result of that objective. I got really comfortable with Ladybug. But now there's a new tool, Climate Studio. The people who brought you Diva have Climate Studio out, and it's a great tool. Works much better than Ladybug, but it costs money. So
right. So this.
He made it. Great.
Okay.
Were you about to say something, Dan? Sorry.
I was going to ask how the new tool, like, so Ladybug is a Grasshopper tool, so it hooks right into Grasshopper. Is the new tool also a Grasshopper related tool, or is it something else entirely?
It's just Rhino, and as a result, it has Grasshopper plugins.
Oh, I see.
So,
okay.
Yeah, so you don't have to get into Grasshopper. You can just use their toolbar in Rhino. But it's really great. It's it sort of feels like a little bit weird because I was so passionate about and still am about Ladybug, and like at PDX or at PSU, I've been teaching it the past couple of terms to their architecture students, and now it's, I don't know, now it's a little outdated. Now there's something else to learn. Oh, cool, Aaron.
Sorry I'm late.
Oh, no worries. I was hoping you'd also show up. I was just talking about Climate Studio and how it's not free.
Oh, okay. I'm not aware of that.
Oh, well, yeah. I mean, you're a faculty. Have you been playing with it yet?
No.
Oh, okay.
Should I?
I don't know. Yeah, I guess it's the latest and greatest of Grasshopper climate analysis, building performance modeling kind of tool. Ladybug and Honeybee had been previously the one that I always liked, but Diva was one that other people really enjoyed. Very easy, but the engine was a black box. But now they have teamed up with or have integrated the Energy Plus engine into their calculations. And it's faster than Ladybug. So yeah. Oh, so I say all that to say, like, is there like I wish there was, can I be like a lab assistant for you or something? So I can get like a card with a student ID or a staff ID even.
What is, what's the name of that thing again? Climate Studio for Grasshopper?
Yep. It's by the same people.
Solima.
Yeah.
Yep.
Solima.
Solima.
Yeah. And Jacob, if I may add, I know all the guys who've developed Solima, with and they're all MIT and Harvard professors.
Yeah, Christoph Reinhardt.
Yeah, Christopher Reinhardt, of course, and John Sargent and all those guys. And I was in LA last February when they launched it. They do like what's called Diva Day. They've changed the name, but anyway, it's a fantastic program, and it's just another evolution. Sorry about that, guys. But yeah, it's a fantastic program. But they, like Ladybug, Honeybee, they all have their place. They all have characteristics and functionalities that make them unique, and still I use them all. With there's certain things that they all just do really well that you can't do in the other one, right? It's like just expand your toolbox.
I'd be interested to hear maybe a little bit more about how you're starting to feather their functions in to your process sometime.
Okay. Yeah. I'm happy to share.
Yeah. Yeah. Thanks all for coming. And do you want to just jump into the presentation, or got any news? Anybody here? Dan's moving soon, New York.
Yeah,
nice.
We'll do hang in Portland.
Yeah.
Congratulations, that's great.
Yeah, thanks. It's pretty weird.
It's Pratt, I assume, right?
That's right.
Awesome. Yeah.
I'll let you know how it goes.
We'll be watching you from afar, I'm sure. All right, so I'm gonna start sharing my screen. Ooh. Sorry, 1 moment. There it is. Okay. So hopefully you all can see my screen now. This is, I guess I've called this parametric stuff. Everybody is seeing my screen? Is that cool, right? Yeah, so parametric stuff. So I started using Grasshopper back in college, in grad school. For my thesis, I was more into electronics at the time. And I came into Grasshopper because somebody told me about Firefly, which is an extension to Grasshopper that lets you talk to Arduinos. And the sliders that Grasshopper had and the interfaces were the cool part, the thing I really liked, and would use them to control these servos and then flex these structures. But then after that, came out here to Portland and started working on a bunch of cool projects. These are just little thumbnails of the different projects that I've done, and we're gonna see some of them. Some of them we'll spend more time on, others we won't. We'll just sort of blast through it, but they're being presented because they sort of mark a I guess a interesting experience as far as understanding how these parametric strategies are can be useful or different, or interesting. So we've got these projects here. So those were, a bunch of like fun projects to do. And again, we'll look at that, but so I'm presenting this. I wanted to, because I hope Eric might be here. Just to sort of show what, the development or direction, or now where I'm at currently, and trying to stay at, and trying to get deeper into using these parametric strategies to explore building performance information. And it's important that, or to me, it seems important that it happen in the architecture office, and that it is able to run concurrently with the design development, because there's often like a 2-week turnaround, and in 2 weeks, a design can change so dramatically, in making all of the any sort of useful information from the simulation or modeling that was done useless. But so really just trying to get these kind of tools in the hands of architects. You don't have to do anything but just hit a button, just feed it information, and it can produce something for you. In order to support this idea, it's not just about implementing these tools, but also you have to go out into the real world and see, the actual building performance. But more than anything, it's all of this design, or the activity of design, is really just more about solving problems and not just making pretty things. But it is a functional, I guess, objective. What we do in architecture is we design and we help implement, we oversee implementation, but we rarely ever go back and test and evaluate and analyze, which I think probably starts to, the design process perhaps suffers, or the object, I wonder, I think about details. Construction details, you put an infrared camera on them and you see how heat is leaking out, and we had a edge of slab detail at Bora that we would just, we've used it everywhere for a long time, and there was just a couple of small adjustments you could make that would improve, dramatically improve that detail. So we did that. We figured that out one year, but it was amazing that it didn't happen earlier. So POEs are great. Rather than qualitative feedback, it's quantitative feedback. Data collectors, you just sprinkle them in the space. All right, so that's that stuff. That's sort of the energy stuff. But this is parametric stuff, and this is the first project that I wanted to show. It's called the Portal, and it sits at the intersection or the threshold of the lobby at a Microsoft building up in Redmond, Washington. People who are visiting the building will walk through this structure, this ribbed structure. It's we've all done the slicing in Grasshopper to structure. This is all made out of metal. It was fabricated by Arctura. They cut all the metal and made all these rods. They made some, I guess, design decisions about, I don't know, some less meaningful details, but overall it was turned out well. I don't know. It's interesting. So there was a lot of input on this structure. It's cool that it's there. And so this is one that I just want to move on through. But what I really appreciate about having worked on this was being able to work with people like Arctura, who can take a model and make something out of it, who can, who are using digital fabrication, methods, and being able to deliver a project much easier. And the collaboration, we prototyped this structure a couple of times. I couldn't find any of those pictures, but that was really great. the documentation for it. Instead of having to draw all these details, you just are really showing where you put it, and then everything else was figured out or contained in the model. So it was just a really different type of project delivery, only for this small piece, though.
Hey, Jacob.
Yeah.
I have a question on the structure itself. Is
Sure.
basically the only connection for this portal at the ground level? Like it swoops and it kind of cantilevers out,
Mhm.
or is that what I'm seeing, or is
Yeah. I wish I
so
had an axon of it. I might be able to find it, but yeah, it's effectively just like a J, structure,
Yeah.
rib that reaches out, cantilevers. It's asymmetrical, or I'm sorry, no, it's symmetrical, but the line of symmetry runs diagonally across its footprint. So in plan, this portal is in a rectangle, and from one corner, front corner to the back corner is the line of symmetry. So we did that just so that we were not having to produce a whole bunch of unique pieces, trying to economize it somewhat. But yeah, it's cantilevered out. They're being held just on those two corners, on those two edges there at the base. That's why that's so beefy, is because they needed because that cantilever is very very heavy, I guess.
So that's what I'm trying to get. I was kind of curious if parametrically you were also looking at, because what I see it from my perspective is I see that the profile or the depth of it gets narrower as it gets closer to the ground, and it kind of widens out as it extends out and cantilevers out. And so it's just, I'm just thinking about weight. I'm thinking about all these kind of stupid details that my brain goes into about optimization of that weight and the stresses and all that kind of stuff. And I know that there are ways for us through Grasshopper and through Rhino to start looking at those types of things and using those as design inputs or feedback mechanisms that allow us to optimize form. But I don't know if that was looked at while you guys were looking at this too, but just.
It wasn't. I wish it was. Back then, this was like 2014. I didn't have then an understanding, or not a strong understanding of. Well, I didn't have Karumba, and I didn't have a strong understanding of Kangaroo at the time. But yeah, so these are fat on one side. They taper, but that's kind of just it follows that familiar language of something cantilevering. You typically see something taper as it moves out, but the shape was more sort of pushed around by how people felt about it. We made a lot of models of this, and just slicing things, and people like this little swoop from the side elevation where you're looking at the long side of it. It kind of has this like haircut swoop thing that everybody really thought was funny. It looked like hair, like I don't know, like Bob's Big Boy or hair. So that to say the structure wasn't analyzed, but cool. This would be jumping into the definition, but so 2016, I had a friend at Ziba who learned that Adidas was trying to find somebody to teach some workshops on Grasshopper and Rhino. And I was lucky enough to get that chance. And when I was doing that, I got to meet some people who were working on a project, this 3D printed shoe, or the sole anyways. The upper changes, but the sole was following a algorithmic recipe that was driven by stresses and not using Kangaroo. And I didn't do it. What was neat at Adidas was to develop this shoe, we're using Grasshopper, but then we're also using these finite element analysis softwares, and there are actual scientists and engineers who are taking samples of this shoe. These are the little cubes in the middle. We would design some lattice, sizing structure, struts, and the organization of the struts that would, and trying to see how they would deform under pressure that you would expect in a shoe, in the sole of a shoe. So there would be an engineer who's just got this machine who's just smashing and trying to destroy this cube, and we watch how it fails and try and then put that information into the model. The partnership was between Adidas and Carbon. Carbon was it is still a really interesting type of 3D printer. Here you can see so it looks like it's pulling it out of a well of resin. It uses a light field to cure the resin, and it's able to produce things very quickly. Regarding using 3D printing. 3D printing is great for making prototypes, but as an actual manufacturing tool, it's impossible because everything takes so long to print. But Carbon, in addition to Adidas, I think they're also working with Ford and maybe somebody else, but they're trying to investigate using 3D printing in the manufacturing process. So this was Adidas's contribution to that investigation. So it was just great to just work with a whole bunch of different people with different expertise, like physical therapists, and again, engineers, mechanical engineers, product designers, people who are runners. They tried out some of these shoes and would report. So this is what one of those definitions look like. On the left side, it's pretty messy, but this is back when there was only one person working on the project. The one person was a really great guy named Jacques Perrault. He's still working on the project. He was the lead designer on it, here in Portland anyways. Over in Europe, they actually have Daniel Piker. They brought in Arturo Tedeschi. I forget. Yeah, I guess how his last name is actually pronounced, but the fellow who wrote the algorithmic, like the quintessential Grasshopper textbook, I guess.
Got me here.
Oh, hey, who's that?
This is Nathan. I was just, that Arturo Tedeschi, that was big book for me.
Yeah, it has all the answers, it seems, like it's just so comprehensive and simple and a pleasure to look through and read.
Yeah, and it's physical.
Yeah.
Got pages you can turn. Great.
And bookmark and dog ears, highlight. But yeah, so Adidas is a very attractive company to work with. So they're able to get some cool people working with them. So yeah, since this initial development, I haven't been working on it, and this all had been really useful to develop the object and the algorithm and the logic behind it. And then all of that was translated into Python. So they've been able to take this, translate it into Python, make something a little bit leaner and meaner, and more familiar outside of Grasshopper world. So I wanted to jump in to one of those definitions. I don't have any of those extensions anymore, or a lot of those components. They're on the wrong computer. So, but it's still interesting to look at, sort of the steps. We were pretty well documented, again, because we were trying to work together. What's that? Oh, okay. Thanks. Sorry. But this definition was used to, you would give it a shape, the design space, the actual sole of the shoe. They call them lasts for some reason. I don't know what the history is to that, but it's basically the space that you want to populate. And you would set that reference. Here, okay, this one's actually I'm sorry, this one's a little bit different. This one, we're using a top surface, bottom surface, and side surface. I wonder. Yeah, so we're just sort of breaking that last model out. That's nice that the data was internalized. So this is, a closed volume. We go through, here's where we start to key unit cell parameters for how you would discretize the space. Bottom surface, let's see if we can't, no previews there. See what that looks. So these spheres were used to discretize the space. The idea was, the smaller ones, it's where there isn't a lot of weight being distributed. Whereas where it's larger, those are the things that those were the cells that we needed to improve. Or those are the cells doing most of the work. Data. So let's jump back to the presentation real quick, because some of the processes, maybe it's easier to see it here. Or actually, I'll jump to the next one. So the image that's all the way to the right side of looking at the top of it. So part of what we're doing right away is, we have the space, we have the boundary, and then we need to discretize the space. We need to break up that boundary in some way. And then inside of that boundary, we'll populate the lattice. How that lattice connects to other, when it changes between lattice types, it starts to morph. And when we jump back to Rhino or to Grasshopper, that's what this up here starts to control. And then the other key thing that I guess we're controlling was the size of the cell, so the lattices, and then the actual strut size. So that's the actual connections, how thick they are. And because Carbon had material scientists working on this project, we could also test out different types of, stiffnesses in the material. But what would have been cool is if we could change that stiffness throughout. That would be ideal, and maybe they can do that now. Maybe not, I don't know. But meaning the stiffness of the material, like the Young's modulus or the actual property of the material to change. But at this time, everything was just the same. And the structure, the properties of the structure were the thing making changes. So just sort of walking through intersections and diamonds, interpolate, snap, and then we do a lot of mesh smoothing. So relax, bro. That was a funny one, which is this giant cluster. It's actually not that, it's clusters inside of clusters inside of clusters. This is a kangaroo, this is a kangaroo cluster. Relax, bro. So it's, we build these struts and then this whole thing basically does what subd does now. So we were stepping through, a lot of smoothing. Those are fine shared nodes, related data to strut. So, jumping back to any sort of reports or data from the mechanical engineers. And that, would generate not only those spheres, but also influence the size of the struts and how that data would interpolate. Generate mesh, prep for patching. And so here's all the final, we're gonna make a model and then send it to Carbon to print. Usually our week would start, we would get the results back from the tests of the samples from the previous week. And then we would spend the week making changes and then send off Thursday for order, the new samples to test. So that was a really fun experience. It was really great to be able to, to work with a bunch of people with different skills. All right, so that's Adidas. At Bora, Bora was a really great place. There was a time they were interested in trying to develop in a way similar to LMN's Tech Studio, like a parametric, I don't know, group of people, people who were interested in these things and could be available to like hop in and do parametric ninja stuff and help projects, you know, I guess be able to take advantage of those efficiencies. So they made a group. It was called Bora. The group's called Laboratory, and it was a small research design group. And this was a fun project that came out of it. We did there were 5 people in that laboratory, and as a way to start, I guess maybe working through what it is that we needed regarding technology and making, we focused on the making, and we were interested in putting together a proposal for a shop in trying to figure out what it is that we needed. We would come together, identify some material, and then everybody would go away, make something out of that material, and come back. And so this was my offering. It was paper, and what I was interested in was just how you could import a curve into it, and how when you roll it up, the shape it would create. So this is looking down on it, whereas the previous slide was looking at it from the side, and this would be the simple sort of process. Here are some examples of it. These are pretty interesting. Obviously, when there's some sort of more, I guess, regular or simple shape, it's much more elegant. Whereas, once you start, once one side, each of these little slivers or space between, once one side and its, I guess, general area or average area, like if I guess what I'm saying is that there's this little neck here is where the problems start to occur. And that's, I don't know, I guess something I never really thought of, or really, I thought that it was going to be a little bit more, I was interested, or it was interesting to see how much the shape was actually fighting itself as it tried to roll. And so this is using Kangaroo. To the left is the definition. And then to the right, it's the different geometries that are coming out of those different groups. It only starts off with a line. It takes that line, flips it, and flips it, flips it, flips it, and makes lines that would indicate or describe what the sides are, their shapes, how many, and the shape of those sides. So in this version, we've got 1, 2, 3, 4, 5, 6. So this will be a 6-sided roll with this sine wave. So we've got the sine wave, and then these lines are what let it roll. Just creases, or all of these cuts are scored using a laser cutter. So there's the intersection, and this is preparing it for Kangaroo. Here's the meshes. This is the beginning mesh, and here's the end mesh. So wanted to, I guess, show that guy off. Let me just open the definition if it's not already open. Paper roll. All right. Yeah. So as I was looking through all my work, I realized I really like this graph mapper. I'm not sure how how everybody else. It seems I always, this is a go-to. You'll see this in almost every single definition I might show. Oh my goodness, it's already 4:40. Well, yeah, we'll go. I'll go as long as you want. So this is the definition. I'm going to run it just so you can see what it can do. I'm going to hit this button. I got to turn this preview on. All right, it's already rolled up. So this is using Kangaroo. This is the Kangaroo setup down here in the bottom. All these are the Kangaroo functions. Putting this together was neat in that you're trying to get it to behave in a way using, physics and I guess that's interesting. Like you find yourself like loading things or trying to float things just to like nudge things along. Because what's interesting about this shape is that the creases, what I have in the Kangaroo setup is these creases that are cutting lengthwise transverse, up and down the length, are trying to be a mountain fold, and this is the math for that. So I can, try and rotate it according to rotate it inward towards themselves. It's a hinge that it's trying to. Let me change something here. I did this for my own, or for the pictures, but I want to get that back to default. Of course. How do you do that? I thought there was a button. All right, never mind. All right. Sorry. Okay. Sorry. Okay, so this is so these sine waves. They're all meant to curve inward. They're using the hinge function, and they're the only ones that are being controlled. And so that's what initiates that rolling. And then how it rolls and what happens to all these little ones who are also hinges, but aren't being controlled, or its angle or motivation isn't being controlled by Kangaroo, but instead just, allowed to flex backwards and forwards. So I'm going to hit that button. I hit true. It's putting Grasshopper or Kangaroo into motion. We can use the slider to just motivate the paper to come together, or the paper model. So it gets close, and I can because Kangaroo, grab it and try and get it to do what I want it to actually do. So these are like mismatched. All right, now they're matched. So it's been cool to be able to interact with the model. And it's been, nearly necessary to be able to grab the model and like push things to get things to just like click into place. Because it kind of indicates how this works as a structure. What's neat about this is that sine wave and how it's working structurally. When you start to impart this, I don't know, somewhat doubly curved, or I don't know what the actual description of it is, but I just appreciate the ideas of how like serpentine walls can be one brick wide, whereas most other times you see brick, it's brick and a whole bunch of cinder block behind it, or three layers of brick. But the serpentine wall over in Virginia, it's just one wide, it's like 10 feet tall, it's very strong, and it's all because it just is a serpentine shape. So that kind of, I guess, doubly curved or periodic, self-structuring is neat. So I guess that was what was neat about it. I was trying to get somewhere with it, but yeah, I'm sure it wasn't that important. Just fun to be able to. Oh, I guess, yeah. So that kind of structure, I guess, when it comes together, it does seem like it needs, I don't know, like it has a little bit of tension right before it snaps together. So it's like I don't know, you need to push it first. It always gets to like some point, and then it just starts to stop. But once it touches each other, then it calms down again, which is neat.
Hey, Jacob, could you
Yes.
go a little bit deeper into the actual Kangaroo definition, like the logic of how it goes through and starts seeing these folds?
Yeah. So all this over here, organize that. I'm gonna stop that, hit that, put that in there. All right. trying to just make sure everything's off. All right. So the first thing, this is all the input geometry being created above. This here is the mesh folding pattern. It's just the mesh and the surfaces that will be used to do some more, you know, we'll get the points, the naked points of the mesh, Weaverbird mesh, but it's really this triangulation that does a lot of the good work, the structuring of the panel. You know, something that is 4 sides is not structural, so you need to triangulate it. Otherwise, it'll be a really typically whenever you see your Kangaroo model, you know, start to jitter, it really has a hard time, you know, trying to keep the that quad, you know, anything that's more than 3 sides, it has a hard time keeping it planar. So most good Grasshopper definitions will, or you should, you know, triangulate it in some way in order to just give that that structure. So that's the folding. That's really just introducing the mesh. So we've got the mesh. It's going over here to show, and that's about it. The points that make up that mesh, you know, are going on to be done to do other stuff, but we're only showing us that mesh. You know, we're showing the mesh. That's how in Kangaroo 2 you see things on the other side. It's nice to be able to say exactly what you want to see. Previously, it was you see everything: points, lines, meshes, anything that goes in comes out, and then you have a tough time of separating stuff. But now you can say on the other side, the only one that you want to see. I only want to see this mesh, and I don't even want to see the triangulated mesh. I want to see the the quad mesh. So so we took that. We're also doing some naked. We're looking for the naked and clothed points. So points that are naked are the ones that are along the edge, and points that are clothed are the ones that are within. The ones that are going within are, I put a load on it. This is -1, so I'm pushing it down. I also got a floor component. So the load takes all of those points and applies a vertical, or in this case, it's a load in the Z direction. You can use whatever vector you want, but that simulates gravity. The weight is an interesting sort of component of this Kangaroo. I understand that there is a specific equation for some of these, like the spring or length of when something stretches, but then other things are more determinate, like floor. That's why it has no weight or strength, which is interesting. But that there are these 2 different forces where one has an objective and another just has sort of a constraint or limitation. So load is one that's applying a force, pushing it down, but then I got a floor to keep it from going in, even further past the 0 point. And then I've got a plane on the XY that I'm keeping some points on. So I've grabbed only those corner points that in that mesh. So I just wanted to be able, keep those points down when we run the simulation, that you'll see those points drag across. Oh, I need to review. Yeah. Yeah, they never really leave the ground, and that's that's the intent. Let's see here, we've got moving down, so that's to try and keep it there. I've got one curve, make like a little track for 2 points. It's between that point and that point, and so in addition to this point being held on plane by this function component, we also got that point being held onto this bottom edge by this component. And I've given them the same strength, so they, yeah, so neither have a preference necessarily. And then some more, you know, trying to keep things like the action where I can see it. We also got an anchor here, which is helpful when you're making it, but you can also like detach it. And now I can move it away. Oh, because it's the mesh, on mesh, I can't tip it up, but obviously, yeah. I think of this thing as more of a cup than anything, than something that's on a horizontal. So, you know, in order to get that, I started thinking about like, well, okay, I need to push it up, you know, I got to like apply a load like that, or maybe I can like blow it over. Like, do I put like a wind in there and like, will that, you know, in order to get it to move upright, or I could just grab it and yeah, flip it up. All right, so floor, that's that. On curve, anchor, plug that back in. And, oh. All right. Length line, these are just keeping the lengths equal. We don't want them to stretch. This is magnetic snap. These are taking those endpoints along the naked edge. Oh, well, just the one, not all of the ones that we see here. But it's taking the points along the edge on either side, and that's yeah, snapping them together. Magnetic snap. You set does that. You set a distance. Well, there it is. You set a distance that it starts to engage, and then the strength. And so this one's actually one of the larger ones because that's important. You know, everything else is pretty small, and they're, you know, not really trying. It's not, you know, none is more important, but I needed that magnetic snap. I also needed to be planarized. Right now, it's sort of kinking right there, but what that side should look like is like the one that's opposite to it. So then, you know, what would be there should be something, yeah, planar, making it planar, some sort of force to make that happen would be useful. And then we've got the hinges going. It's got this really useful component. Typically, you would have to do some whole bunch of like crazy path mapping and relative, you know, tree management in order to get the right points to create hinges. But Daniel Piper's included in Kangaroo these hinge points, which makes it quite a bit easier to break up and associate points in order to describe a hinge. To say what one hinge, so there are two here. There's one for the small, for the vertical, or for the horizontal ones. You can see at that input there, we get rest angle. There's no input. It's just allowed to be whatever it wants to be. Whereas this hinge here has a rest angle, and that's the one that controls these sine curves. That is controlled over here. So it's pi times, you know, 0 to 1. And that would indicate from 0 to 180. And depending on how many sides you have, this can, I guess, do different things. But, you know, one that makes sense for 6-sided somethings. But if you get into something like, it's just for fun, I'm gonna say the length is, make it just a little bit longer. I want to add more sides. They're overlapping with one another. So I've got this little thing to try and thin things up. So that's all that. I can even, yeah, I guess adjust this if I wanted. Just to, yeah, do it just to do it. Hit the reset button and run it. So one, you know, is 180, and you can see that. It doesn't look like what it should want to do, but you need, yeah, that control is motivating them coming together. And so once it comes close, yeah, you flatten it out again. Yeah, you like get in there. And but yeah, I get so this is sort of an interesting, I get, way to explore those models, and really just to see whatever what shape would this line make. I have the graph mapper who's controlling those, but you can input whatever curve you want, and it'll do the same thing. Make a bunch of them, flip them appropriately, match it to the surface, and then run the simulation. So that's the last thing. To say something about the hinge and how it works, it's actually really super simple. And that's, I don't know, I thought it was more complicated. Or I guess yeah, I like its simplicity. So it's got 4 inputs. It's got the fold start, fold end, tip, and tip 1, tip 2. So it's looking for where the hinge is, that line of the segment, and then tip 1 and tip 2 are going to be tips on either side of that line, and it's just evaluating the vector or the angle between those 2 tips relative to the hinge. Yeah. So that's that. That's all that stuff, and then yeah, we merge them together. For whatever reason, show is usually separated from everything else. And it's usually not, and you would put it in the second branch. I've seen it in some, I'm not sure why, but I see it in some definitions and sometimes I don't. But I know, but I also know, yeah, if I put show into the first branch, it doesn't work. The simulation doesn't work if I were to flip the 2 inputs. Show would still work, but yeah, I guess I just don't know what's happening in the actual solver regarding trees. But if Daniel Piker's putting show into a different branch, none, I just do it, I guess. Yeah, that's all that. Yeah, any other things that anybody wants to see or questions? Or,
Thanks for sharing, Jacob. That's super cool. That's an amazing definition.
thank you. Yeah, it's pretty fun. I don't have my laser cutter anymore, so I don't get to make these as much, or play with the actual physical object. Because again, it's not just making something here. It's taking it out and seeing how it, making it in the real world, and making it, I don't know, discovering it as a physical object, and in as much being able to bring that back to the modeling and perhaps do something better, or improve the model. Yeah, so these are all the other inputs that you want to see. Okay. So it's 4:58. Yeah, how is everyone?
I'm good.
Yeah. I mean, yeah, let me, I'm gonna just sort of, real quick, just kind of blast through some of this just to show you. And if any of this looks interesting, perhaps we can, take a close look at one of those definitions, or one of these definitions, or something else next time. I don't have anything planned for your next meeting yet, but so this is just a screen wall. It's Interlocking Boxes. It was made for University of Washington's Global Innovation Exchange in Bellevue, Washington. Yeah, interlocking boxes, and their extents are being determined by a graph mapper. Here are some axons of what both sides look like. These people are doing sort of something I imagine they would do. Where one side is long and sort of a sweeping curve, and the other side a little bit more. It creates a smaller scale where perhaps people can sort of just nest or hang back into its armpit.
Are your fabricators doing install, or is one company doing fabrication and another party does installation?
We work with Superfab on this one, and they both fabricated and installed it. They have a shop on Belmont, CNC routers, and they've got their own design team, and working with them is great because they you can share models and definitions and collaborate.
Yeah, bridging the gap between design and install can be the real project.
Yeah. I mean, yeah. Well, in public projects, you don't have the opportunity because you don't get to say during design who is going to install it because, public bidding. But you can get consultants and you can write into, the spec performance objectives that only one company can meet, but you can't partner up. So only in private projects can you do that. And the reason that we got to do that with this, it's University of Washington, public schools as I know it, but because Microsoft and was involved, there was a different pot of money that we got to play with. And so we're, making feature elements throughout the space. And this was one of them there in the lobby. Again, yeah, here it is in the lobby. Here's some dimensions. About, 15.75 feet long, 5 feet wide at the base. What I learned from the portal that we saw in the other first project, a lot of the shape was also not only were designers' opinions and aesthetics, but also code played a lot into it. There needing to be cane detection in certain places and head banging issues. So this shape, it's again curvy, and so I decided I'm going to just make the base super wide, so cane detection issues and head banging, issues are just gone. You just can't get to it. So that was nice. Yeah, and the interlocking came from their logo. I thought the logo was cool, just like bringing together this intersection of things, and so we suggested it as the construction method of the screen. So again, it's just individual boxes. This is sort of the map, alphanumeric, A, B, C across the top, and then 1, 2, 3 down. Again, this is about as much documentation as we needed. In fact, I just included it in the sheets because I thought it was cool looking. But really, Goodmod has the model. He had these cut files, so they actually don't need to see anything. Those won't be the documents they'll use to produce the model. This is again the definition with what's being generated. We start with a XZ plane. We create a grid of points, the regular points, regularly spaced, that is, evenly spaced. Then we host our boxes onto it and rotate them 90 degrees or 45 degrees so that they're, oh no, I guess 45 degrees, sorry. So that they're more diamond shaped, an X, like the logo, yeah. So we take then the discontinuities of the corners of each of those boxes and shoot it out in 2 different directions and, or extrude it out. So, you can make a box in 1 of 2 different ways. You could use a line and extrude it, or I always like using points and then making lines. Always doing trying to do all of the manipulations to the lowest geometry I can, I guess, instead of creating something with booleans, that's going to be an impossible definition. Whereas if you're just moving lines around or points around, you can have a super fast definition and just save all the other stuff for the final. So this kind of works that way. Yeah, so I mean, I'm creating boxes, but I only want those points. Yeah, so I decompose that back to points and then shoot them back and forth and create new boxes. And these are lofted together, and they create a single surface, open B-rep, and then the last step is thickening it. And then the step beyond is, laying it out for fabrication or just sending the model to Superfab.
So did you thicken it with the notches built in part of the geometry then?
Let me, I think I got that one too. Let me jump to that, because what I used was there's just the region intersection component that comes with Grasshopper. So, and that seemed to do the job just fine.
Okay. Yeah, I was thinking that would make it run slow too.
Yeah, I have like I don't know, cool pictures of, or a bunch of pictures of different process models that are interesting. But okay, so here's that definition. There we go. Okay. All right, so we've got something here. Yeah, if we zoom in, we do see that there are some, yeah, just lap joints, simple lap joints. And how that is being made is just using this one component here. I'll shut this off, zoom back out. So we're looking at this component, which is those single surfaces, the boxes after they've been lofted, the two rectangles lofted together. We've got that open B rep, and then we decompose it so we can have those individual faces. This is the part that I hate about this definition, and or it's something that I guess I find unsettling because when I flatten it, I'm flattening it because I want all the boxes to, you know, intersect one another, but that also destroys the tree and its logic, and that to lay it out later, I need that tree. So that makes this definition, I guess, a little wonky. And that's I guess if I were, you know, to try and improve the definition, that would be it. But this works just fine. So we have those boxes, we decompose the surfaces, and then we're intersecting them. That component just, yeah, finds those intersections and and then creates lap joints. So it's creating them along the edge of the different surfaces that make an individual box, and then slot joints. The way it's doing this here, the original definition is quite a bit messier. And one of the reasons why is because this kind of intersection and the way that this is being extruded is a little bit different than how we actually did it. You can see that the edge of the box is set back from the edge, whereas in the actual model or in the real thing, they sort of come together. What's that?
Is that because is that the ending at the center point from your point cloud?
What I did before and what I didn't do in this one was what we learned when we made this is that those intersections are really sort of tough to work out or fabricate. If you can see my mouse, I'm sort of running around an area of it's sort of an issue that we didn't, I guess, understand. Because we're making this box, but we're cutting it with a doubly curved sort of surface. Instead of, in the definition, projecting those discontinuous or corner points forward, which is, no, that's not it. Move, yeah, that's it. Okay. So instead of shooting those corner points forward, being driven by, numerically being driven by these two graph mappers, they had been projected onto a surface that was created by the graph mappers. So what that means is just that because it has two different, I guess, reference points regarding that termination, or the way that it would, the way that ultimately how that intersection expresses here in this version is different. And it would be easier to build, I think, and we would be able to avoid what were pretty awkward things going on here at a lot of corners. And when you're, I don't know, when one thing's off and it's off by so little, but it's repeated, a couple hundred times, things really are unexpected. And Superfab was great in that they were able to manage that. But the face of this and the way that we had created it, created the face of it, and their machining capabilities, there was always these, what happens here would be really awkward when you have like that short flat side of plywood exposed, and then it runs into something else that is sort of turned on a different, turned according to a different plane, you know, that's coming from the surface. So yeah, all of that. This one was, so it's a different construction. This also was different in that you can't slide the boxes in and out of one another, which is, I guess, the other thing that seems very necessary in order to stay true to that, I guess, construction method. This idea.
Yeah.
Yeah. But yeah, so I was going through these definitions, trying to clean them up, and that was one part that I started to like have different ideas about. And in order to make the curve thing, you know, and to improve it for today, I don't know, I guess I just thought maybe I'll, yeah, kick that down the road a little. But there is a video that's neat.
I saw that assembly you put up on LinkedIn.
Yeah. I've been, it's pretty, I think this is it. No, that's not it. This guy. Oh, I know. There, yeah. So for anybody that hasn't seen it, I love, this is a cool video. So Superfab, they fabricated it, all the pieces. They put it in boxes, they put it into a box truck, and they drove it up to Bellevue and then unloaded it. They started early in the day, through the video, watch the light coming in through the window and how it changes. So they're, you know, start by bringing in all the pieces and then, you know, staging them. And then they move into assembling the base. Then they'll go around and secure the base into the slab. And that's about as much seismic. That's about as much seismic we needed to do. The structure itself was, there's so much, you know, all these boxes and boxes, you know, interlocking with one another. It is very structural. And so our engineer had no concerns about that, just only, you know, making sure it doesn't, you know, move in case a earthquake were to happen. So now that they've got the base made, they put down the first layer and they, yeah, tighten it up. They use lamello type of, they're really interesting joints or like biscuit joints or tools. Yeah, you can lock things together and make furniture and really nice cabinetry with these concealed things. And then that's how fast it goes up. Yeah, they're just locking them, pushing them together. And that's cool. Look at that light.
Yeah.
It hasn't even changed. Like, I don't know how long it took them. I know they were there for 15 hours total, but it looks like that. It just took them, I don't know, two hours. And so what they're doing now is adding these little tabs that, so when the boxes interlock, there's this large tongue, you know, you might see in the middle that occur in the middle of the, yeah, this like tongue that happens here. And it was a weak point. And so what Superfab had come up with were these little pieces that would bridge, you know, the tongue to the outside so that they wouldn't flop around.
Oh, I see. Yeah, they wouldn't line up, or they'd get kind of pushed aside in assembly.
Mm-hmm. Yeah. You can, I mean, it's not, I liked it. You can barely see them. Yeah,
Cool.
So yeah, there's these little, I guess, nail heads or covers where those lamello joints are. You stuff them into like what would be a typical biscuit cut into the side, and then you can use this Allen wrench that comes into the side and locks things together, pulls it in tight. They're really, really neat, expensive, but it's perfect for this kind of stuff. Cool. Well, yeah, I've got, yeah, plenty more. This is the other same project but different thing, making super graphics out of fabric and pegboards. That's cool. That was a fun one. And then got an auditorium. This was the one I actually included it for you, Nathan, where I was looking at frequencies and ray tracing in order to try to, I guess, understand or talk with our acousticians about what they're looking for in shape, in the shape of the theater.
Do you know Keith Yates' design?
No.
They're doing a thing where they integrate ray tracing for like above 200 hertz, and then they go into fluid dynamics models for low frequencies.
Interesting.
Yeah. He's got like crazy PhDs on his team, but
sure. Yeah. I'm just, there's,
wow.
I imagine the tools for researchers and tools for architects.
Yep.
I just want them to be pretty and easy so that architects will, maybe play with them. So I found this useful in being able to, it was really these cheek walls here that we were looking at that I wanted to understand a little bit more closely or geometrically, and to be able to, just might as well just make the whole thing parametric.
Yeah, so you're looking at first order reflection distances?
What I'm, I guess, indicating here is the different frequencies that are being used, and the type of the size, and being able to say what is interacting with those frequencies based on the size of that modeling element. So, like a base is going to go right through anything that's under 20 feet. Under 20 feet, and it's just going to basically interact with the boundary of the ball of the shell. But those other frequencies and the elements in the space, I'm trying to make some determination about its using the dimension of those elements and those frequencies dimension to say if they touch or bounce or do something, interact.
Cool. I like the color coding for the frequency. And also tie those together and index them.
Mm-hmm. And then the other part, so that was the overall shaping, and then the interior screen and what that might look like. We started looking at diffusion. This is I'm not sure what pattern this is. I think it might be the one that I eventually looked at, but a quadratic residue diffusers is so it's an interesting math. Yeah, Nathan, you know what it is. Getting a modulus, it's basically the remainder of a division. So if I divide 3 into 10, the modulus is 1. Because it divides evenly into 9, and then the remainder is 1. When you enter a sequence of numbers into a function where checking the modulus, like 1 mod 3, you'll have one remainder 2, or we won't have a remainder, so it's 0. 2 mod 3, the remainder is 1. 3 mod 3 is 1, or it's 0 again. 4 mod 3, so actually, it sounds like mod 3 is kind of a binary pattern of outputs. But when you start to explore that math, you can get all sorts of really fun just patterns. And and here's a sampling of those. And I used the laser cutter, cutting the sections and layering these things up, layering up sections in order to make these little models, just to look at really the light and shadow. I was interested in looking at that specifically and how these textures. So these were really pretty, but they're all just very small. So what's different about them is that they're all using a different mod number. So you put in a sequence, and then a similar mod number will create similar patterns. But it scales up and scales down. So you see, like this one, we're scaling out. Like there's that circle, but now there's all these mini circles, and now there's these even smaller ones, and now it's like binary, where it's just a checkerboard, and then it starts to come back into focus, and sooner or later it returns, which would make sense, but mathematically, seeing the patterns that come out of that map is cool. I like the there's diagonal ones too. Yeah, definition, starting with a surface, doing the ISO trim, getting rectangles of a certain count, or yeah, I guess cells rather, discretizing the 2D space with a certain count of cells. And then using that function, I'm just offsetting those different cells in different ways. But the number sequences are running in either a U direction, or which is to say a local X direction, or a local Y direction, or a combination of the two, where it would be an array. So when it goes along the X direction, it's vertical. When it goes along the Y direction, you'll like manifest it horizontally. And what we're seeing here is it going in both directions. So it offsets, and then this is a fun part where it then subdivides each panel, again using these graph mappers, and then using a graph mapper, just applying some, making some holes into it. Zoom in a little. So you have these individual panels. We're dividing some of them only 3 times, some only 2, and some multiple times, and all of that to then cut holes into them. Oh. Oh, yeah, that is the whole one. Oh, okay. Yeah, it's hard to see in this picture, but yeah, again, I have to jump into that definition. Scatter screen. So that's what it looks like. And we're up top. Yeah, we start with, as we saw in the slide, I guess, yeah, we don't have to go through it here because it's kind of more, wanted to show you the, okay, this part. So looking down at it in plan, we can see the preview. Okay. So starting on this side, we can see, we're just looking at the individual cells. If we were looking at this in 3D, we would see that they're already offset up and down. And what we're doing in this group is creating or dividing up those cells into more cells using the graph mapper. And so if I change it, yeah, you can hopefully see, oh no, let me, okay,
So,
more clear.
okay, it's like one UV division becomes a function of the other one. It's not random. They're kind of crossing.
Yep. Yeah.
Cool.
Yeah, and you're able to dictate or control where it occurs, using these sine waves or just the graph mapper. You can use different type of. So it gives you the same look, and then
Fill up
the
those
minimum.
alligator skin.
Right. Yeah. Make purses or boots. So that's sort of a fun aesthetic. Jump back in. Hey, come on. Oh, it's probably not named perspective. Oh, perspective 2. Okay. Yeah, so we can see how we can start to tie or maybe have things react to their depth. But this is the part where it makes holes into those different regions. Grab this. Like that. So the input is what we saw above. That. Oh, is it making holes? No, I think I'm still in the same spot. What's happening here? Offset. Yeah, no, this should be where the holes are. Oh, I guess they are there. There's something. Oh, this is on. All right, that's why we're not seeing. Okay, sorry. There we go. Preview on. All right, there it is. Yeah, and we're so again using the graph mapper to make holes. We can say we're offsetting that, those smaller cells in. We're locating them or just generating them using the graph, like selecting them using the graph mapper, and then the slider to say what the uniform offset is, which is important when it gets real small. Some of those cells, an offset like 0.1 can throw an error, but the very end here is just extruding the form or extruding it so it's now a 3D thing. I put some lines too, just for graphic.
So Jacob, in your definition here, the one where you're doing the holes, that's just using the graph mapper. It's not. It's more of an aesthetic algorithm as opposed to it being something that's being driven by, let's say, acoustical information. Is that what I'm?
Yeah. The input that the acoustician was offered was the. I'm trying to find the section here, so there. Oh, and I'm in InDesign. The only direction they had was don't put any or a lot here. We need that hard surface up front, and so that told us, as at the design or how this radiation happens along the side was guided by that. It just diminishes as it moves forward into space in order to provide more hard surfaces for early reflections. And that was it, really.
But they wanted these kind of perforations along to sort of help with absorption and reverberation. Is that what?
The holes were less important. That was more for aesthetics, jumping up. So here's what they look like. What we were, what we were more working or having more feedback on was the way the panels or the pattern that happens along the edge and the depth and sizes of things. Basically, they were telling us when it becomes a problem. Other than that, we could just do whatever, show it to them, and they could tell us what they were concerned about.
Okay.
But that was really about it. Yeah. It would be cool to do, I guess, something more performative, but it's hard to come up with the right data or feedback without, needing an engineer. And then I just continued developing it to make it just something cool and wacky. So it's the same logic, but this wasn't ever an option that we looked at. So I think I actually showed, I think everything. Boy. That was it. That was the last one. Cool.
Awesome. Thank you.
Yeah, this is awesome. So on you building these definitions for this project you're showing right now,
Mm-hmm.
how long did you have to sort of explore this, and how long did it take you to sort of develop the logic and troubleshoot and sort of get the results you were looking for?
I did. So in addition to doing this actual work, I was, doing the more typical architectural design and development of the auditorium, and also the music rooms, the music room, the band room, and the choir room. And then they have a stage craft area, and then a green room. So like, the whole sort of performing arts part of the high school, me and a project architect were primarily responsible. And I guess with perhaps more design influence, I started looking at this outside of anybody's particular direction, and outside of normal work hours. I got excited about having acousticians I could ask questions about, and I was encouraged by the principal of this project to do some research into it. So without much knowledge about it, I started looking at, surfaces, architectural elements that would be most influence the acoustics of the space. Understanding that there's reflection, there's absorption, and then diffusion. So reflection is just like you need everything on one. Everything needs to reflect, and absorption is everything needs to absorb. But diffusion, there's a really interesting space there. And after building all of these modern, theaters, we realized only then acoustically they turned out to be subpar, mostly because they're devoid of ornament and this smaller sort of crenellation that can interact and create unique diffusive experiences and a more unique, I guess, quality to the space. Is, I guess, the only thing that made theaters different is diffusion, or the spatial quality. Mostly wrapped up in that. So all of that, that's why I started looking at diffusion. I eventually found the quadratic residue diffuser and that math, and then fell in love with the patterns, started making all of these like little test samples, again, just because I was curious, but showing them, and using them as a way to talk to the acousticians, make sure that I was on the right track, sort of looking into something, but having the consultants, the real experts to guide you was useful, and having that opportunity felt like I took advantage of it, and had a cool project come out of it. But yeah, so it eventually made it into the project. We needed to do something against the sidewalls, so and we had all these little models I had been making, hanging around. So we started looking more closely at developing it, or marrying the two.
Super cool. Thank you.
Thank you. Yeah, man, I'm really happy you guys showed up, and I was able to share this. Cool.
Sorry.
Oh, go ahead. Oh,
that was awesome.
Thank you.
Thanks for showing that. Man, that thing you did with Superfab is amazing. But whatever happened to that piece?
It's still there.
Oh, really? Oh, it was permanent. I thought it was like for a show, like a temporary thing.
Oh, no. Yeah. That was a part of a renovation. So again, that was like an architectural, like fun element inside of a real project.
Cool.
And so we renovated or built out really a space up in Bellevue, and it's now called the Ballmer Building after I guess he's not still the CEO, but the previous CEO of Microsoft. It's still there. In fact, when I shared this time lapse, some people, Nicholas Ames, who's the makerspace director up there, saw it and reposted it. It was my first LinkedIn repost, so I was really excited.
That's awesome.
I'm reaching people. But yeah, it is really awesome. I'm hoping to the Goodmont. I'm not sure if you guys have ever heard of them, but they're a local. Spencer, I've been talking to him. He's interested in running some Grasshopper classes, and he knows had seen the GIX wall, that screen wall, and thought it'd be cool to learn Grasshopper and then learn some tools and make something that you bring home, and thought that would be a fun example.
Yeah, that's cool. Yeah, he's been looking at Grasshopper for a while. I've actually never met him, but I've met so many people who know him. It'd be great to get in touch with him and get him to be part of this,
Yeah, well, I've got him slated to present in August.
Oh, awesome.
Yeah, he's gonna show some stuff. The guidance I gave him was just what's cool is that he's looking at Grasshopper, but he has all these machines to play with.
Yeah,
and he does a lot of cool projects, works with a lot of cool people, a lot of cool opportunities. Worked with Holst on Winter Lights Festival. Works with street artists regularly, and then he himself is making some interesting furniture. And he's got this geodesic dome. he's got a clay printer and nobody knows what to do with it. I think he used to have a robotic arm and nobody knew. He would just buy things and just try and like, does anybody want to learn this? I want to learn. And sometimes he'd have time, sometimes he doesn't. But he is really interested in trying to put that clay printer to work. So if you ever, if you wanted to do something with that, it's gathering dust on US 30 right now. In his warehouse over there.
That's too bad.
Well, I haven't seen the inside of that warehouse. I just he put a sign. I think he's had it for a while, but he put a sign up, and that's where he has some of his larger machines, the clay printers there, or messier machines.
Yeah, cool.
And I've been trying to schedule, or I'd like to schedule, go over there and visit. So I don't know if you'd like to get included in that.
Oh man, I'd love to see that. Yeah.
Okay.
Field trip.
Yeah.
Field trip.
Yeah, it's opened up. Yeah, we're all vaccinated, or I'm vaccinated, so I'm cool. But, yeah. All right. Well, I'll get in touch with him about that, and maybe just send out a doodle or something.
Do we have a plan for next month?
So no.
I've been just learning a lot of Python stuff. So if anyone's interested in like a GH Python.
Yeah.
Four of us.
You just volunteered. So, yeah,
that'd be awesome.
I can do it like my previous show and tell where I'm pretty much running through files and running my mouth. But I don't know. Yeah, depending on who shows up, people's background or not, a lot of it's going to be like the kind of rudimentary stuff, but a lot of stuff I was spinning my wheels with before I figured it out. So let's do that.
Awesome. I'm going to be personally looking forward to that.
And Nathan, did you know Python before you started that process, or was it?
Nope. Honestly, I've been kind of like Grasshopper dabbling a little bit, and then last year my company laid off a bunch of people, and I was like, I need to make machines do the work for me now.
Yeah.
And like I started Python probably in October. I'll share all my resources that I used to learn as like part of the presentation. So some books and some online, and I did like, first I learned some Python just discretely on its own terms. And then I started learning GH Python and some of the nuances. So, not the best at it, but I once I got into it, I'm like, I can't believe I wasn't doing this before. So it's really, really powerful.
Never found the time. I tried to learn Python and failed miserably, and I haven't really gone back, but.
Well, with everything, I hit a point where I'm like, oh, I need to use this to do something that I really have to do.
Yeah,
and then, like, that was what really flipped it. So, but yeah, Jacob, I'll keep in touch, and we'll set up something early next month.
Okay, awesome.
Cool.
Yeah, thanks for suggesting and offering.
Yeah, I just want to keep this group going. It's awesome. So.
Yeah, me too. Cool. And trying to be better about scheduling things. Like you could ask 6 people in a week and you've got 6 months of scheduling done. So I put that together finally and realized like, oh, I gotta email some folks. So Spencer being one of them, him presenting and perhaps a field trip could be 2 different events. But then Jeff Sosby, who's a architectural designer over at Lever, was I got him. He had been working in New York at In Situ as a digital fabricator and has some pretty cool projects he could show, and definitions. I thought it's cool to look at definitions and see how people do things. Like, and looking back at my own definitions, I realized like I used to move points a lot instead of just putting them there. Instead of just like, if I want my point, like instead of moving the origin point wherever I want it, I just construct the point there. And I guess maybe, 2 ways of getting a point to where you want them to be, but that kind of, I don't know, seeing how those kind of steps or logics or how people are getting through their sequences, if there aren't any efficiencies or, I don't know, better practices or something.
Yeah, I find there's an obsession because it's like, when you start learning it, it's about learning to put control on everything. So I'm just like, okay, every single point has to be able to have a slider or something. And
yeah.
And then you're like, why do I need to do that?
Yeah, you sort of, so forget what it is, what's important about the control. You just end up making a more complicated model. But And I guess to that end, yeah, I'm going to throw up all. We've got that we've got a shared Google folder that Dan set up, and he's in the past we have been using it as a place to share files, and I was going to throw all of these up there today. If you guys wanted to take a look, and
yeah, that'd be great.
Yeah.
So I don't know if I ever got an invitation for that Google Drive. Was that through the meetup? Or when we?
It was Dan set it up. Dan set it up through his Google account. I believe at the time, he just emailed it out to everybody. But we can put a link to it somewhere on the meetup page so everybody can be aware of it and access it easily. When I do that, I don't know if I have to coordinate with Dan. If he has to send out emails to specific people to allow them access, but when everything's set up, I can shoot an email and let you know, or let everybody know.
And I know on the last call I couldn't make it, but a colleague of mine, Andy Brandt, I know he wanted to be here. So the recording today will be available through the meetup.
I'll put a link to it. It'll be uploaded to YouTube.
Okay.
Yeah.
Excellent.
Yeah, Andy, I was thinking about Rhino Inside. He talked about that at the last meeting, and I agree that would be an amazing topic to go over sometime. But I don't have Rhino Inside. I need a faculty ID from PSU.
Are you doing freelance now?
No. I'm looking for a job, but yeah, not that I'm not looking for freelance.
What are you looking for? Are you looking for an architectural position, or are you looking for something that kind of dabbles into what you're researching now?
I would like to learn more about what I'm researching now, and Eric, you and I've talked before, and had, I guess, excitement. What I felt, and it energized me, to know there was somebody out there, but also a lot, and just wanting to, I guess, wanted to, I guess I had this idea that to email you sometime and ask if there might be a way I could just look over your shoulder or understand more. Eventually, I would like to become a certified building modeling professional, building BEM.
Yeah, a bit.
Yeah.
I mean, I'm happy to, let's keep the conversation going, and happy to share what I know, and let you grow if that's the direction you want to go. That's cool. I mean, you're doing a lot of really cool stuff that kind of blows me away. That's way beyond form making that I don't have the skill set. So we're learning together.
Cool. I have been interviewing with a couple of people, got the chance to share some of this work, and what's funny is they're impressed, but there's I don't know what to do with that. And I think I need to either figure out who wants something. Architecture, it was a unique place I found at Bora, but in developing that way, it seems like I'm becoming less of an architect. They're looking for people who have a broad range or set of skills, and not that I don't have that, but the thing that I decide to showcase is this, and potential employers who are architects don't know what to do with it. But Adidas and Nike use these kind of modeling tools. Other Daimler, car companies.
Company? You mean the Daimler, like the Mercedes Daimler?
Yeah, just making molds for grills, and then.
Oh, interesting.
Yeah.
Huh.
But it starts to you just start to turn into a modeling, thin monkey kind of a thing. I would like to stay in architecture though, or I'd like to be around architecture and buildings and construction, and do more make it, put it out there, measure it. So, and starting to think that might lead me to academic life. But I don't want to move all the time. Every time I get a new job, I don't want to have to move across the country.
Yeah, understood.
So if you ever hear anything,
I'll keep my ears open, and if there's something that I think that's a good fit for you, I'll definitely try to send that opportunity to you.
So you have Rhino inside there at your studio then?
So, it's kind of funny because I have two jobs. So I have my performance consulting firm, and then I'm also the sustainability manager over at GBD Architects.
Oh.
So I've just got too many hats. But the thing that I'm trying to do at GBD right now is I'm trying to change the culture there to include more Rhino and Grasshopper thinking, eventually allowing it to be a integrated vertical process where we're looking at design and the production of the BIM models all in one kind of workflow. So that's where Andy comes into play with trying to kind of understand Revit inside Rhino, Rhino inside Revit, however you want to classify that. And so it's sort of kind of this thing. And I mean, we have a little research group at GBD very similarly, but you guys were doing a lot more experimental things with that folding and really cool form making that we're not really dabbling into. But regardless, it's super, super cool stuff. And it's the future of architecture design. It's anybody who's not doing this stuff, even with what you're doing, Nathan, with the Python. In 5 years, if you're not doing this, you're a dinosaur. It's just going to be one of those things to, it's the same people who didn't adopt Revit and were using AutoCAD for all this time, and they were just kind of forced to have to acquiesce and accept the technology. But I think if you want to be thought leaders and out in the marketplace, this is where it's happening. This is the front lines of it. So that's my personal belief.
I believe I have a similar thought in trying to encourage people to adopt these technologies. It can be a struggle, but and eventually they do. But sometimes, there's this fledgling community, but a tool like Rhino inside it's a game changer. And that, and like you're saying, it's almost, people won't be able to avoid it anymore. They're just, especially now that Rhino's inside Revit, and everybody uses Revit. Before, people would use SketchUp, and to use these tools, you had to, learn a completely different software. But because everybody's already using Revit, they'll be a lot more comfortable just adding one extra add-on and getting used to it, which will be great. Yeah, I'm looking forward to that too. Before I left Bora, I had started putting together some projects. One was to simplify the Revit models coming out, and then sample or look at the materials to those to the elements. So taking 3D geometry, turning it into geometry, like eggshell modeling. And then also being able to identify what material it's made out of, so you can do some carbon analysis using Tally, automate that, and then and then create an eggshell model for energy modeling. And then the other thing I wanted to do was, I always met any architecture's firm portfolio or any portfolio to the treasure trove of information if you know the right questions to ask, and thinking about using Rhino inside to look at all of these Revit models and, just sample, query them, gather up data, and then look at it to see if there are patterns or, useful information. I think about schools mostly and program proximities, and what year did the makerspace become such a common, element or program piece in schools. And being able to look back from anything that's a Revit model or any sort of to look at 2D models even, or 2D drawings even, could be possible, but to try and harvest that data and take a look at it. There's no doubt there are going to be just incredible insights.
I don't know if I have your latest email. Maybe it's embedded in the meetup, but can you send me your email contact information, then I can contact you if I see any opportunities or know of anything that.
Sure. Yeah, I'd be happy to do that. I'll made a note of it. I'll send it to you right after we get off here.
Awesome, man. I got to run, guys.
But yeah. I really appreciate everybody sticking around for us. Yeah, for all of this. Thank you.
Yeah. Okay. Have a great day, everyone. Bye.
Thanks a lot.
Yeah. See ya.
I'll reach out and we'll figure out next month.
Cool. I made a poster for this one. I don't know if you want a poster or some sort of a event, or would you like to make one? Or
let me see. Yeah, I'll make one.
okay.
I assume there's no specific. Is there? I don't know. I'll look up if there's any graphic standards for the proportions or anything.
Oh,
Make a
for yeah,
project out of it.
yeah, right, yeah. Cool.
I rarely interact with all the different like Portland Python meetups, but I might drop an invite too and see if we can get some lurkers too.
Yeah, yeah, that would be. It's likely they are, you know, they're aware of Grasshopper, or I almost want to change the name of the group so to include maybe more just computational design and parametrically design. Whether they're using, I saw Aaron was using Blender recently, and it's, or like Unity, it would be cool. Or
Yeah,
anything.
there's a lot of like self-selecting for architects because of it, I think, and I think there's a lot of other interesting crossover stuff. I've written scripts just to like solve simple acoustic stuff that I just use as a calculator. It's like a visual calculator, and I can just slide a thing and figure out solve for KA, whatever. And so it's yeah, I think it's one of those things, those tools, once you get used to it, you just start doing everything. So
right, yeah, when you have a hammer, everything becomes a nail.
totally.
Yeah, yeah. And I guess if you're already in that space, then yeah, you don't have to go to a different program to go.
I know. I'm gonna start like writing birthday cards in it or something.
Talking to Spencer over the weekend, he actually alerted me to a couple of cool extensions that I otherwise wouldn't have heard of. Something that was useful to people who are furniture makers and product makers, and making finely detailed items. Architects don't use, and so I forget, one links you into Houdini, which is a really powerful modeler, but there was another one called N-topography, topography, and similar to what SubD does, and what the modeling for that 3D printed shoe. It does a lot of like discretization and all of that sort of mesh modeling, really, and finite element analysis, structural analysis.
Definitely want to get more into the FE stuff. That's
it's like being able to actually get data,
totally
making meaningful decisions.
Oh, one more thing. I think maybe I mentioned it a while ago, but like a good flex for people who are like, pretty stuff, what do I do with it, is, I don't know, 80% of what I do, I think, is actually figuring out manufacturing efficiencies, or like how assemblies work, and getting like, cut a bunch of stuff, make it self-index on itself so assembly goes together better. So
yeah,
that's a thing I've definitely used in job finding. So
yeah, the documentation and tedious tasks, and like, let's free up time to do the fun stuff. Let the computer do the tedious things.
How do I make this easier for people? Real sales piece.
Rhino inside, again, it's just like you can really just make a button. And actually Python, it was even better for that button. But yeah, cool.
All right, I'll talk to you guys later.
Yeah, see ya.